today. So we've met quite a few times. What I'm showing here on my screen are the notes from the last time we got together. We did skip the last week due to, I can't remember why we skipped it. We skipped it though. So I've started to do just a summary at the top for the people who just want to know what we're up to. And I've made a new category called Awaiting Review. And so we can check those during the week. And like I said, last week we presented with Jamal about P4TC and the welcome message to everyone. And if we want to get into the weeds, this is the Too Long Don't Read, and these are the things we're working on in the GitHub project, and the slides from last time, or little snips from the slides. So I guess I was going to start with 5 or 10 minutes ahead of time and maybe go into, did anyone have PRs or anything you wanted to cover first before we go into the second part of P4TC? So what I can show you guys here is, if you can hear me okay. So I have the to-do list, a couple of items that are in draft, items that we have in progress, and let's see here, and then here are these awaiting review ones. We're either waiting a review from someone in the community or, looking for a cross-reference. These are the items we had done this week. And, oh, I'm in the wrong view. Okay. And then here I needed to check with Murcha on a couple of issues here. So Riff, did you have one you wanted to cover before we go into P4TC, or Andy or Chris or anyone?
No, thank you.
No? Okay, all right. So these three that are waiting for review, this one here, for example, I think it was, oh, this was me. I was trying to create a change to some documentation, and Riff and Marian told me that there would need to be more downstream table changes. So that's what that one is. And then this one here, that refactoring coming packet and cap handling, this just needs a review from Marian. I don't think I see him on the line, but if he comes on later, I can check with him. So, okay. And oh, last thing I wanted to share with you guys, just project management related. I found this new view. And so now you can see, during a certain time frame inside a GitHub, you can check your active PRs, merged, closed within the last few days. You can do a month, 24 hours, 3 days. So I haven't seen this before, but then this will say who's pushing the changes and what those are. So I may start to incorporate some of this kind of graphic into the weekly meeting notes. I'm not sure. I need to explore a little bit, but it's a handy tool for me. So anyway, I'll go ahead and turn it over to Jamal if you're ready.
Yeah, I can share my screen.
Yeah, please.
Okay. All right, there you go. So I'm probably going to repeat some of this stuff from last time. Just
I can see. Mm-hmm.
Right. So the workflow, I described the workflow last time. It generates everything in green is generated by the compiler. So this is the P4TC backend of the compiler. It generates what we call an introspection file. Maybe I should show a bunch of these. Here's an example of a P4 program. Very trivial. It has a table that just an exact type match. These are our annotations that we use, mostly for if you're writing a CLI, etc. It will be able to you will be able to understand what IPv4 means, and that it's going to be called prefix. So you have a table that does a lookup and has one action. Sorry, there's two tables: the next hop table and the fib table. And if you look at the logic, you first look up the fib table, and then the next hop table. So the next fib table derives an index that you then use as a lookup key to this table. So the generated files are what we describe as the introspection file. This thing here looks like that. So it will describe the program name, the pipeline name, whatever, the tables, what the sizes are defined. We even have number of masks can be restricted if it's an LPM table. The actions, the parameters. So you'll see these are the annotated names. The type, 48-bit, mostly someone typed using human readable octets for MAC addresses. Then the CLI or the API will know how to interpret that, devices, etc. And then the eBPF code that gets generated, which you shouldn't be looking at unless you really have to, looks something like this. And this is all on GitHub. An important detail is this thing we call the template. So the template matches this piece here. It's a bash script that generates the pipeline, teaches the kernel how to manifest the pipeline, the tables, the actions, the extents. So I showed that. This is the template file that you're seeing here. So a simple DSL that will say go and create a pipeline. It has 2 tables, and then if you iterate through all this, all the objects are manifested to the kernel, which then uses them to at runtime. And I'll show the runtime piece again. The BPF program is what I just showed you. You compile it, you create a binary blob, you load it into the kernel, and now you have a software data path. You only need this if you want a software data path. If you don't want a software data path, the alternative is you create your binary blob that gets loaded to the NIC vendor's spec. So there's a backend compiler for the vendor that will create all this stuff. Okay. Any questions on this? I mean, we separate the parser to be something separate.
So you said the introspection is compiled of all of these pieces inside of the routing. Yeah.
Yeah, it describes the names, the types of the different objects, and it gives them IDs. The compiler generated ID. There's an interesting discussion on what happens when you have IDs. How do they get interpreted by the hardware versus software?
Jamal, is it safe to say that introspection file is sort of analogous to P4 info, but it's sort of enriched for this kind of backend?
Yes, I think it's very close to the P4 info with our own special annotations that our APIs understand. So the APIs will suck this. I'll show maybe an example of an API call. The CRUD APIs basically then become aware of the objects, what their types are, what their identities are. So when you do the runtime control over here, yeah, actually this shows it better. Maybe I'll put it in full slideshow here so it looks better. You can see that your API typically should be sucking in the JSON file that matches your one or more of your program names, and then your CRUD it's a given. Basically, you literally don't have to write this again. You write it once, and you can keep changing the program names. So yeah, it's very close to P4 info. So yeah, so going on to like I was describing earlier, this piece, this green piece, this is what you saw. I showed an eBPF program, but it could be XDP or it could be both. If you don't want software backend, then you don't invoke this backend at all. So sorry, you still invoke this, but you do not you don't load the eBPF program at all. So it could be entirely hardware based, in which case this part disappears. The objects that you manifested that I described earlier, these objects, and I showed that template bash script, that has to be present all the time. That's what teaches the kernel what the different objects are. So this is optional. And this is also optional. If you only have virtual devices that you're just running the software data path, then you don't have a NIC that supports the driver constructs we are requesting for, then you can't get the hardware to work. Sorry, yeah, go ahead, Chris.
People might be interested to know why this backend has interesting promise compared to other software backends that we're aware of, like BMV2, you know, it's kind of limited and a little bit slower. And then there's P4D-PDK, which we've got some knowledge of in this working group. You know, we're hoping to use it at some point when it's the gaps are closed. The one thing about this approach is you've got a potential continuum between pure software and hardware offload. For example, if you had an ACL table or some kind of a, you know, mapping table that had 5 million entries, it's possible that that part could be offloaded to specialized DPU hardware, correct?
Yes,
And
absolutely.
and from the 20,000 foot view, it would still be the same program and the same workflow, except that part of it could be running on hardware at hardware speeds, and the parts of it could be running in the kernel. Is that a fair statement?
Yes, absolutely. Thanks, Chris.
And
Please
this
interject.
is really the only workflow and architecture so far that I've seen work that way.
Yeah, and so you're exactly correct. Once we manifest the objects in here, they could be used either you could split between software and hardware. So you could take half your table. Maybe there is a software. When you add the entries, you specify whether you want them to be software only or hardware only, or as a best effort, you try to add them to hardware, and on failure, they get to software. So the software could be your exception path, because the hardware may have some limitations in terms of capacity, probably. The other thing is it could be actions that the hardware can't express that you probably want to do in software. So that's what we call the split mode. You could also just do hardware only or just software only. I think the big value proposition here is you can test this on a laptop, really, or on a VM, and when you're ready, the only thing you need to change is your control plane invocations. I'm going to show maybe an example here. This shows an example of how someone would add a routing entry. This is a CLI. This is not what you want to use for scale, but it shows an example here. I'm going to add an entry to the desktop table with a key index. This is all annotated. If I showed you the P4 program, you see this is annotated. So the CLI already knows what this is. It can query the JSON file. Next hop index of 1, an action called set next hop with a parameter destination mark and a parameter port. And when I add these entries, I can ask that this entry goes only to hardware or to software or to both, or to try hardware as a best effort and software as a fallback. So so we can have the split software. We can have the mirrored decision whether table is consumed by hardware is made by the control plane. And there's a variety of other approaches in which you can split things. I'll describe in another slide. I'm not sure if that helped. Chris, did I?
Yeah, I think that's interesting, and some other context that you wouldn't be familiar with, but there's this feature, this concept called bring your own data plane, and that's been, and Riff's been part of that definition quite a bit. I believe he brought it forward. I'm wondering if down the road this might be a potential way of implementing bring your own data plane to Dash. So it's outside of the scope of today's meeting, but it's in the back of my mind.
Is that data plane considered software only, or it could be a hybrid between hardware and software? Or
well, this just brings more options to the table, I think.
Yeah. Okay, so the control plane, I went over this last time, but I just want to emphasize it again, that we have a CRUD-like API. So we have a verb, and there's a handful of verbs. Actually, there's there's 7 verbs. It could be create, read, update, delete, subscribe, or publish. An event could be published by the kernel, and the control plane could subscribe to events. We sort of adopt the path, the noun, from something that looks like a Unix path. So here's my program. Table is the object. Control block 1. The table name is my table, and you could specify a key, probably with a priority. I need to fix that. Or if you leave out the key, then you're referring to the whole table. So here, for example, you're dumping the whole table by leaving out the key. You could create a single entry or create a batch of entries. You could delete. You could literally flash the whole table with one command by replacing the get here with a delete. There is an object, there's a wire format that comes from Netlink on how all these commands will be laid out in binary format. The APIs look as follows. So you create and you provide the path to the object. You could have one or more pieces of data if you're batching, for example. You could read and provide an optional filter, which is an interesting interface. It looks like a select if you're familiar with SQL. You could update. You could delete and specify an option. You could subscribe, also specify an option. And the example here shows an example of how the filters would work. This is the select equivalent. So you could say monitor any P4 events that have a command create. So anytime a create is used on a table called tname3, tname3 is the table, which is under the control block called CB in the P4 program, and filter by observing that the action that table entry was using that was created has a parameter called dmac based on the P4 program, again, which matches the following. Right, so you don't have to watch every event. The kernel will filter everything, so there's nothing crossing from kernel to user space unless you have a match. You could also, this is very useful for aging out things on occasion. So you could, or just flashing things that have, you could send a command like on this table name, table 4, I wanted to delete everything with a filter that no activity was seen in the last 10 seconds. This is in milliseconds. So those are the APIs, and maybe I could show a very quick example of a program. Here's one that subscribes, just so you can see the APIs. So you basically define it, and this is not ready for public consumption yet, but I just want to show it so you can get the idea. You create a context. You then initialize. This is the API that sucks that JSON file. It looks at the P name, which is your program name. This is just a toy example, but it will give you an idea. And you say, I want you to go and look at that. I don't care what the command is. And I'm interested in the P4 runtime object. So you get your attributes back, and then you specify a filter on that object that you retrieved here. And you specify the substring name. We have a little filtering language we came up with. And so there's your filter. That, of course, will be transformed into binary before it goes out to the data path, into a binary format. So that's your select, basically, right there, the one I highlighted. And then you just issue a subscribe, and this blocks until you get a response back. But we have also the concept of callbacks, where you can provide a callback that gets invoked every time an event comes in. This is a very trivial. The default callback is something that just prints on the screen or on the console for you. So that's one way to use filters. I mean, if you want to do a create, same thing, you grab your context, you add your key to the attributes. We have this concept of whodunit, means in order to track which program or entity that is allowed, added the entry to the data path or deleted an entry. We log these things. The APIs, you can ask for an acknowledgement back, or if you don't specify, you don't get an acknowledgement back. You can ask, in this case of create, give me back what you actually added. So I'm going to send you a command, but once you add that table entry, echo back to me what you added. Because typically a create is a one-way asymmetry. Basically, you send your data to the kernel, and the kernel just sends an acknowledgement back. But in this case, for debugging purposes, you may want to get back the echo. And then you issue your create. So you can see all our APIs start with p4tc underscore and then the CRAD command. In this case, it's a create. You saw the subscribe, and then you wait for a response, or you could register callback. Sorry, I just rushed through that, but coming back to this, that's the API I was describing here, right? That, like I said, we have a little bit more than a handful of APIs, right? Any questions on that? Or?
Looks like we're good.
Yeah, so extends, yes. So extends are, I'm not sure how much Dash uses extends, but in particular, custom extends are important for us as we realize this is the best way to extend. We're dealing with a host kernel environment as opposed to a middle box. So we need a little bit more richness. So I can quickly show a diagram of how an extend would look like. Here's an extend that looks like a register. So the templating language that I described, everything in green, is generated by the compiler based on a P4 program. You run this, it creates it manifests the structures for your extends. In this case, for example, an index table that looks like a register. And then and as you get more complicated, as your extend gets more complex, you may need to write a kernel module, right? So this document specifies complexity of different extends. These are more and more. So we studied a lot of extends and came up with this interfacing, basically, right? And the rest of this document will say how we annotate things. The one thing I should probably have mentioned is we have this concept of permissions on what the data path is allowed to do or not, and what the control path can do on a specific table entry or a specific table. This was mostly to address the concept of const tables or const entries, but we just did it differently. We could disallow the data path even to read or write a table entry. Or maybe it can just read it, but it can't write to it. We have several annotations that we came up with that are listed here. Like, we have an ACL, which is the permissions for the extends, but it's not just specific to extends, it applies to tables as well. We have different concepts, whether something can, this is just an aid to help us generate the code appropriately. I don't have time to go over this. If you want me to talk about this, I can come back for it. Mm-hmm. But you can see some of the generated extend code. This was a trivial example. It's just something that has a constructor and one API that it invokes, one method. And it's instantiated in the P4 code as such. And that's what the template gets created. Here's the eBPF code. And here's the Linux kernel module implementation. So in the future, right now you have to write this module by hand, but in the future we're going to generate this code. At least the majority of potentially possible code that could be generated. So there's a lot. Yep. So any questions on extends?
Yeah, I think
No.
Custom externs are pretty exciting because it lets you express things that P4 might not be able to express using the native constructs, or you might be able to do it much more efficiently. We've had add-on miss type things in the Dash behavioral model. We've discussed ways of writing that in P4. And it's always been an interesting discussion, and a custom extern might actually make some things easier.
Yeah, true. And it's a lot more efficient sometimes to write the extern in C as a kernel module than it is to write it in eBPF.
Yeah.
I think we have a work item for digest message extern for BMV2, Chris.
Yeah. So we do support digests, I should say, and we do support add-on miss. So digests do work fine. I don't have time to give a demo, but you can describe your digests. Okay, if you
so
want.
It was Jamal. It was last May 2024 where we were talking about possibility of defining extern functions for P4TC, and we have talked about it in the past.
Okay, so digests are from a control plane API. They're just events. You can have, using the subscribe API, you can actually subscribe to many control plane applications can subscribe to the same or different digests. And we do have a sample utility using TC command line, which we call, where you just run, you say TC monitor P4 digest, and it will monitor every digest. It will receive all digests in user space. Okay, any questions on that? If you're interested in this, I can show some example, maybe even run a demo, but I'm just trying to rush for sake of time here.
Yeah. We've got 32 minutes left.
Okay, I can come back to it. Let me see how
Okay.
much I can go. So
Okay.
deployment model. Let me put this in a bigger screen. So this is, I'm not sure if Dash sees the devices the same way Linux would do. So this is an IPU/DPU. These are the ARM complexes, an out-of-band port. I think everybody now has an out-of-band port, as far as I know. It could be a BMC as well. And of course, you have the match action engine here. That's P4 looks at. And you could have optional accelerators doing crypto, compression, etc. And so we run, and of course, that's the host. So we have two modes of operation. One is you could turn it into, and as far as I know, at least the vendors have access to the hardware for all support this. You could run it basically as an FNIC or a DAMNIC or a SmartNIC, where you have no access to this. Everything is, the control plane sits here. So we call that the SmartNIC mode, where you just, your control plane doesn't even sit here, it sits there. So when you're adding those P4 control messages, you're literally going through these interfaces and dealing with this ASIC. But these two are mutually exclusive. You can turn that off, and this I believe is done in the firmware, so that the host has no access directly to the ASIC. I should have mentioned that in the SmartNIC mode, these ports, we call this the switch dev model. The ports have representatives that show up in the host side. So as you can see here, we have these virtual ports. Some people use, well, there's two concepts. There's the VFs, which are part of SROV, or the SFs, which are more shared devices. And you get a copy of those devices. So they're twin pairs, basically. So the key is the model is you can put this in a container, you can put it in a VM, you can run it on bare metal, you can put it in a container inside a VM, and you're controlling everything through the ASIC, right? Which container gets what, which container inside which VM. All those things appear as ports as seen here. In the case of the switch SmartNIC mode, the physical ports as well, where you connected the cables, do appear on the host. So when I do IP link list, I will see these ports. If I turn off the SmartNIC mode, then I'm running an XPU mode, in which case I don't see those ports, right? And I do see these because these are shared. These are sort of mutual. They're not mutual, I'm sorry. They are twins, essentially. And on the ARM cores, I get to see these ports. They get abstracted here. So my P4 program is aware of them as well, right? And the model for running it in software or hardware is the presence of these ports dictates how we do this. So this could be purely on Ethernet. I'm not sure about InfiniBand, but definitely anything with RDMA, Rocky V2, virtual ports, loopback port, vEth, those all work with P4TC from a software perspective. So any questions on that?
Sounds like no.
Okay, so basically what I was describing as either the TC-eBPF hooks or the XTP hooks could sit here if you're running an XPU mode, could sit there, and could totally be missing altogether. And all you're doing is controlling access to these devices through your P4 control program, which may be just programming this thing here. All right, so optional. This could be optional if you don't have hardware that supports P4TC or the P4TC network driver blocks, so network driver callbacks, I'm sorry. And I showed this diagram earlier, but I wanted to show it alongside this so that you can see that how it applies to that. You have ports, you can run P4TC, that's the TC model, data model, basically. Okay, if there are no questions, I'll move to the next slide. So this is how you deploy it, all right? So how would you test this? You would write your P4 program. again, going back to that diagram here, write your P4 program, generate the eBPF code, test it on a laptop or a VM or a container. When you're ready, you also generate the same equivalent program, and there's some challenges in that you put in hardware. And then you can decide whether you want to have an exception path in software, some parts in software, you want to split your pipeline, you want to have two different programs. The exception path could be a totally different program, P4 program, and it has nothing to do with what's in hardware, or variations of that scheme. Right? So I guess the value prop here is you could test this on Rocky v2, on a soft Rocky, on a laptop or a VM, and then deploy it on a hardware offloaded Rocky v2, as long as if there is need for sort of P4 kind of constructs in there. Any questions? Okay, I'm going to take
Keep
that.
going.
Yeah.
Right.
So,
Silence is, silence is assent.
Yeah. So I was going to show some sample examples here, some sample programs. I think I started showing this one here, but we publish a bunch of them. I just haven't had time to do a lot more. But here's some stateful programs. I think since Chris mentioned add-on miss, we do support add-on miss, and we do support these profile IDs, etc. First, look at this. It's a simple flow tracker program. And you can see that add-on miss equal to true here, and that on timeout we would actually notify you. So there's various. I see Andy's here, but there's various ways you can specify what should happen on an idle timeout of a table entry. You can have it be deleted and notification sent to the kernel. So in this case here, you're just saying, well, just notify me. I will delete it. Our default is, if this is not specified, is we're going to delete it, and then we'll let the control plane send an event to the control plane to say it's been deleted. So it's a trivial example. Like I say, if it's TCP, then you grab your metadata from the source destination port. You run your control table flow table here, which is that. Upon a miss, a new entry gets added. Right? Just says what the protocol, etc. And your control plane is there's no control plane in this case, because this is just a trivial flow tracker which would count, let's say, the bytes and the packets using a counter. Right. So if I was to, this example is showing that I'm running NC, and here is an event that if you're monitoring events, you'll see something like this pop up. It will show you the different tuples in the table, the aging timeout, whether we created this as a constant table entry using the template language. You could add entries in the template, and what the byte values are. And if you decide you want to retrieve the counters can be expressed. If I know the counter ID, the key is 6, I can actually go and retrieve counter only number 6 as an extern. And at some point after an idle timeout, you'll get an event like this, which says it's been deleted. All right. And here's, like I said before, if I specify just a path, I can dump the whole table. I can also dump it in a JSON format if you want to have an interesting parser. This is a utility. You should really write your own control plane API. Like I think last time Chris was saying, Psi tends to is very CRUD friendly. So you should be able to write something that would be able to use this API. So those are some sample programs. I could show more depending on what the interest is. But yeah, this one is does IPv6. Your classical examples is an ARP responder, right? You could extend it to be also responding to pings. You got a routing example. just as IPv4 routing decrements TTL and forwards the packet. You got some example of tunnels like IP. Some other, the classical calc example, right, where you can write your own custom headers, etc. And you, again, statefulness, I was showing an example here for that could be trivially implemented as well, like a layer 2 switch, which is a learning switch. So we have a program like this. We just haven't been paying attention a lot to it. It may have bit rotten a little bit, where you could follow this logic and then do the FTP updates and at runtime, basically, in the data path, right? And our goal is also you could let the packets go to the kernel, have an eBPF that instead of adding the entry through the control plane, would add it through here and say, I want it to go to hardware. It just goes through our API, basically. That would be for hardware that doesn't learn in hardware. So if you have some, I know some ASICs, you could do the statefulness in the hardware, and some ASICs maybe you can't, but that's, you will have to let the packet go to the kernel, and then the kernel will add it through the APIs, what we call the K-funcs here. The other option is, the other reason you may want to send it to the kernel is because you want to add some richness. Maybe there's a lot of stateful derivation of your stateful data from a lot of pieces from a lot of components. Then you may want to let it go through because it'll be a lot trickier to do in hardware. Any questions on the implementation? Oh, sorry, on the examples.
None from me.
Okay. So someone asked about performance numbers last time. So we just, Victor just ran performance numbers yesterday. These are definitely not the final judgment, but because we have a lot of optimizations, we're not fully paying attention. So this is on a bare metal Intel Xeon. It's about 4 or 5 year old machine. We have the simple L3 forwarding, which I kind of showed, where you see it from the network, you parse, you do a lookup, you do your TTL decrement, and you pass it back to the network. So it comes in from the network and goes, and we allocated just one CPU. This thing has 26 cores, 2 hyperthreads, so 50. You could look at it as 52 CPUs. So we're essentially using like a one hyperthread. It could be maybe a core. Well, I'm going to say it's a core. So there's differences between LPM. LPM is slightly more expensive. And you can see that with one core where we had 4 million entries. I picked this 4 million entry because I think I saw, now that I'm getting the emails from the GitHub, I saw someone changing the LPM, one of your LPMs to 4 million. So we did 4 million. Mm-hmm. But our traffic generator is only sending 130K flows that are distinct. See, we're hitting about 850 kilo packets per second at the TC level. So just to remind you, mm-hmm. The TC level means we're running on this. So there's a lot of it. The packet has to go through a lot of code in order to hit this part here. So it's a slower piece of code. And it also using the Linux buffers called SKBs. Whereas at this level, they're not converted yet. So the SKB has a bit of has an overhead. So you'll see that XDP is always better for simple programs. Once it gets complex, the distinction is not that high.
Yeah, I was wondering, so with LPM, you're not doing any ACLs at this point?
It was just a single LPM table.
Single, okay.
Yeah.
Have you considered injecting policies?
Yeah, I have some data on
mm-hmm.
You're talking control path performance, right?
Mm-hmm.
Yeah, I do have some data. But this is on one core. It's a toy. Sorry, someone else was asking.
I also have one small question on the proof numbers. So do we support a recirculated packet, and how will that impact the performance numbers?
We haven't tested recirculation, but yes, of course, it will add these numbers will go down if we have to go through a very long pipeline that requires recirculation. But yes, we do support recirculation. If that's, I guess that's the
Okay, so we do support recirculation. Okay, great.
Absolutely.
Yep.
Yeah, you might have mentioned in the first meeting, Jamal, this is supporting the PNA architecture.
This is PNA, yes.
So whatever is an architecture you can do more or less, or will be able to do.
Yes.
Yeah,
We-
architecture-wise, I think it is supported. Just like not sure if the, for example, like XDP backend, if that is actually gets supported.
Okay, so XDP has some limitations. You know, there's
Yeah.
there's some there's some things you can't do in XDP, although it's been getting better. The concept, for example, of broadcast, I think it now exists. You couldn't broadcast packets out of XDP, but you typically would split your data path into some, generate code that runs in both, right? So you'll do the hard stuff here, and then this supports recirculation. I'll have to look whether with the current constructs we can do recirculations here. This is a lot trickier to do recirculation. Okay. So going back, sorry.
Have you looked at the scale of what we're doing with Keysight, Ixia, and the hero test at all?
No,
Like the number of prefixes and ACLs we're trying to shove through?
I think you mentioned a number last time after the
Mhm.
control plane. You didn't say what your data path is. And remember, this is software, right? I'm pretty sure on a 26 core we should be able to hit a minimum packet size 64 bytes, probably 25 gig. I'm sorry. With probably average packets, we can probably go all the way to 100 gig even. Like, you know, whatever on bulk transfers, where the PPS is low, we can do much higher. But it's software. You would not. I wouldn't use this. Perhaps the bring your own data path that Chris was mentioning earlier. That, you know, someone doesn't need more than say 25 gig, then and willing to pay for the CPU cores to do it. Right.
Gotcha.
Right. Otherwise, you get overwhelmed. Like you can see this core at 850 kilo packets per second. All it's doing is forwarding packets. It's doing the parsing, lookup, incrementing TTL, recomputing checksum, and sending it out. And you're already killing.
So you're not popping the header, decapping, de-encapping.
No.
Okay.
No, I think that would be slightly more costly. I just put some. We just put up some quick examples to.
No, it's fine. No, it's great. Thank you.
If you have some suggestion on what you like tested, we could do it.
Right? Okay. Yeah. Thank you.
Yeah, but again, these numbers will be much better than BMV2. They would definitely be not as good, probably. I'm pretty sure not as good as DPDK. With the advantage here is we're not dedicating the CPU to poll and nothing else, right? So that CPU could be used for something else unless packets come in. Okay, so control path. I think this is where the interest was. Again, these are numbers using LPM. So if I mention to you here that we do have these APIs, right? And that we can batch. The one thing I think I should have mentioned here, you see, we can batch things. And we can thread this code. So this example application that we used here was written in Rust. But, you know, you can pick your favorite. Well, we will support Rust and C and probably Python. So I'm showing you just one thread, meaning we're only using one CPU. We can do about 185,000 per second. There's a lot of room for improvement here, but we're not rushing that. It hasn't become a priority that we have to improve the performance. Okay. 380 if we now use a batch size of 16, right? But still with one thread. If I take that code and I make it 4 threads, meaning I'm running over 4 CPUs, then you can see the numbers go up. If I take that same code and I add a batch of 16, the numbers go up, right? So there's room for improvements. You could play around with this number. You could play around with this number, and you could probably get better numbers than this. But this was just to give you an idea of what happens. Deletion is in the same realm. Some cases it's slightly better. We haven't looked at the performance, the perf outputs to see what is going on. But again, there's some things like you know, one of the things I described earlier is everything is you give it a table path, and you could ask it to delete everything. And so this now, I was hoping for much higher number than this, but this is what we're hitting right now, about 2.5 million deletes per second with a single thread. Right. So any questions? Okay, so what's your numbers, Christina? You say, I think you threw a very large number at me last time, something like 10 million per second.
Mircha, can you chime in here, Mircha?
Yeah, I mean, it's the minimum 3 million, I think, per second.
These are ads that you create, right?
Ads, yes. And you need to expire them every second, so you can say adds and removes.
Right. So would you say that batch is acceptable for those tests, or this is individuals?
Individuals.
Individual, yeah.
Yeah. So our numbers there are lower. I'm suspecting that if you use DPDK, which has direct access, you will probably get higher numbers than this. So on boot up, do you have, when you boot up the device, do you do, and when do you add these entries? Is this a runtime thing, or is it on boot up you want to add 10 million entries or 20 million entries or something like that?
But just to understand here, this we are talking about flows in the table as that, or API calls?
No, these are entries that are added. The API call will have data. It will look like. So when I say create, I'm specifying the data as well. When I say batch, the plus sign here means I could send more than one table entry with one create command.
Yeah, this is analogous to loading the initial config for hero tests, not dynamic add-on misbehavior. Talking about two different things.
I mean, in that case, we can batch a lot if it's loading the config. I thought this is about adding flows in the table while the traffic is coming. I thought this is about the P4 performance.
No, that should be high. We haven't tested that. You mean the add-on miss kind of interface, right? You're talking about the
about the dash pipeline processing part, not about the API, not about programming the pipeline.
Right. So something like if I have a table like this, then when I look up the table and if there's a miss, I add an entry. Is that what you mean, or in the data path?
Yes. So if those creates can be bashed, I think that's good if it's in millions per second.
Yeah, so this one is, I don't know how you could do batching here. I'm not sure. You could, but I'm not sure what the effect would be. We'll have to buffer maybe a little bit until you have enough to batch. Or this one's when we add on miss, it's every individual entry. So
no, that's how it would work in production. You can't really batch the add-on miss because you can't predict them. They're just coming in real time.
Yeah, yeah.
So yeah, we've got two different conversations here. One is the initialization, which, as we've seen, that can be a challenge through all the software stacks. And then there's the dynamic behavior. And, to be fair, that question about how many connections per second, we have to say, what context is that in? Is that in a software kernel implementation? You wouldn't really use that in production for Dash because it's not going to ever keep up with DPU hardware. You'd have to compare it to a DPU implementation, to be apples to apples, like comparing it with, a hardware version where the code's been very heavily optimized at great pain by the different vendors to make it work on their platform. And, that's one of the most challenging metrics of this project. And so it's all highly optimized using every trick in their pipeline and software and hardware both.
It is an interesting question. We'll do the number. We'll try to measure this. So in our case, basically the add-on miss API. This API, which in eBPF would be what we would call we have a K-func for it.
Yeah, it would be interesting.
Yeah.
We don't even actually in Dash in the behavioral model, we don't have this add-on miss because we're using BMV2. So it's just something we don't do. We test the packet transformations basically, but we don't, we can't really test dynamic behavior. So this gives us a tool to possibly do that if this were ready. And it might be performant enough to do meaningful test even in CI/CD.
Yeah, I think we can probably benchmark this and just say how fast can we do this in software. It will depend on many factors, what the CPU is, how much, what the RAM frequencies are. There's going to be.
Chris has a very good point, because if we compare it with BMV2, then it's way better than BMV2. And if we are talking about production, then you will do harder offload, so the numbers change.
Yeah, so like I said, the main advantage here is you could test this. You could test your P program as is on software, and it should just work on hardware, assuming that the APIs are, the vendor supports.
Yeah, it provides that continuum we've been looking for.
Yeah. So for testing or for building like a digital twin that may not need a lot of throughput numbers, you could definitely deploy this on VMs and containers in a cloud somewhere and do all your testing. And for a distributed system, and then it works. It will work the same way in theory. I mean, there could be quirks here and there in hardware.
Maybe,
for example.
maybe you can be our guinea pig, Jamal.
So we are looking at thanks to Chris, we're looking at Dash. Chris,
thank you.
Yeah. I would have to say, let me just jump to that slide maybe, and then I can come back to these other ones. So here, ongoing work, complete support for Dash. So the problem is where we got stuck is Dash wasn't compiling. So there's these two things. One, 28-bit arithmetic wasn't working, and var-bit parsing and extraction and deparsing. So we're fixing this. And we're working with Intel, I should say. I should give credit to the Intel P4C compiler people.
It's okay. We broke P4DPDK also.
Okay. So we're keeping them a little busy on this and other things. And I suspect that when we start running Dash, we'll see some issues. Right? So we may be missing some features. It's not obvious until you start running it to say, why is it behaving this way? Or there may be some quirks in Dash or in our implementation that have to be aligned. Right? Yeah, so basically these are control plane APIs. So do you not use control plane at all, or is that this interface, you don't use that?
We use P4 runtime to
P4 runtime
in Dash, for testing.
Yeah, will be a lot faster than P4 runtime. Unless P4 runtime is back ending directly into the hardware then and bypassing the OS abstraction. But yeah, and I do believe we're more flexible than P4 runtime. I think it's great work. I just don't want to put it down. And I don't know if Andy was involved here in case he gets upset. So we have time still, Christina, or?
I think we're about ready to wrap it up. We've got 4 minutes left, and usually like to give people 3 minutes to their next meeting. But I can see the challenges here, and please go ahead for one. Yeah, go ahead for another minute or so.
Yeah, I was going to say that there are some challenges in the case of sometimes the hardware. You want to write a P4 program that works both in software and hardware, and depending on your creativity, maybe the hardware doesn't support some things, right? So those are kind of challenges we're running into. And it may require that perhaps we annotate the program to say this only works in hardware.
Well, yeah, we've run into that. Yeah, we've run into annotation issues.
Yeah, you say, okay, this table only works in hardware. Don't bother trying to do your table.
I think that Bud or Excite Labs talked a lot about that in the past. Yeah.
So there's always this mismatch that that we're running into now that we're actually looking at hardware closely. So and other challenges. So we have different approaches of how this is going to be solved. I can stop here.
Yeah.
So,
Okay. Well, thank you for everything and for your time. And I hope everyone got something good out of this session. I'll go ahead and stop the recording. And Jamal, please feel free to reach out to any of us if you need in the future. You know where to find us now, Wednesdays at 9 or Thursdays at 10:30.
And our goal is to get Dash as a use case to work on this.
Oh, that would be great.
Once we go past the compiler issues we have.
Okay. Yeah. Please let us know where we can be targeting our efforts. Thank you.
No problem. Thanks.
Okay.